I'm Charles Wilson, Staff Product Cybersecurity Architect at Torque Robotics. This presentation will cover the Secure Settings Identify Options activity. This diagram shows the overall AVCDL training path. If you're taking this training, it's assumed that you've already completed the AVCDL overview training, and additionally, that you've completed the Requirements Taxonomy, Security Requirements, Secure Design Principles, Apply Secure Design, and Secure Settings Overview. This training will cover the Secure Settings Options Identification activity. Before getting into option identification, let's briefly review where it fits in the overall secure settings process. Here's the secure settings process, which we've previously covered in the Secure Settings Overview. Our focus for this training is going to be on the first activity, that of option identification. Within the Identify Options activity, the Security SME is going to take the tool documentation, examine it, identifying any security options that are there, and create a tool security options document. As a reminder, when we're talking about cybersecurity-relevant tools, we're talking about linters, compilers, static analyzers, fuzz testers, and dynamic analyzers. These tools either reason on the code directly or work with instrumentations of the binaries produced from the code. In either case, they expose issues which are going to be cybersecurity relevant. Now let's work our way through an example of a tool's cybersecurity-relevant option identification. We'll be using the AVCDL tool cybersecurity options template, which is described in the accompanying tertiary document that goes along with this training. It's important to note here that this is just one mechanism for documenting this information. There are any number of ways this information could be documented. In an ideal world, you'd use a database to store this information both across tools and versions of tools. For our example, we'll use the GCC compiler and extract its cybersecurity options, or at least a subset of them. Specifically, we're going to be talking about GCC version 10.2. This brings up an important point because as tools evolve, their options can change. Similarly, it's important to know what the platform is. There are going to be some tools and some options of those tools which have no applicability on a platform of interest, and so evaluating them would just waste time. Next, we'll have the location where we can find the tool and information about the tool. We record the SME who's doing this investigation, the date that the document was updated, and finally, a monotonic and increasing version number. The next, and arguably one of the most important steps, is that we're going to document all of our references. This is the documentation used to identify the cybersecurity-relevant options. It's comprised of a name, a description of the document, and its location. We see here in our example that we call out GCC 10's general release information. We've got the online documentation for GCC 10.2. We use the C++ core guidelines, the C++ programming language standard, and finally, the MISRA C++ 2023 guidelines. Now we move on to enumerate the tool's cybersecurity-relevant options. Our example will only include a small subset of the available cybersecurity options. The options available in GCC are extremely extensive. This step is probably going to take the greatest amount of time, because the activity requires that the cybersecurity SME appreciate both the tool that's being used, in this case the compiler, and also the capabilities of the tool that are important from a cybersecurity context. Here we see that we're giving each unique IDs. We've prefixed these with GCC so that we can later use that ID to identify the tool. We provide the option as it would be used, and last, the options description from the documentation. Once we have all the options enumerated, the next step is to indicate what their relevance is to cybersecurity. This doesn't need to be an elaborate explanation. As you can see here, we're using short, concise text to explain why the option is relevant. Our next task is to assign a bug class to each option. We're going to be using the NIST Bug Frameworks classes mentioned in the overview training. As covered in the overview training, the NIST Bug class has three categories that it puts these classes into. These are input, memory, and data. Now let's get into the specifics of what each of these classes focuses on and what concerns we have with the bugs that can come from each. For input, we have two classes. The first is validation, and our focus here is on the format of the data that's coming in. And our concern is data corruption and command injection. Here, the input is not what it should be. Say, for instance, you have a field that you're expecting a numeric value to be put in, and it gets a string. Alternately, you expect a simple string to insert into a SQL query, but you get a compound command. The next is verification. Here you have data, which is of the correct type, but the value is not in range. And this can give us incorrect behavior. Say you're using the input as an array index, and it's well beyond the range of the array. That's going to give us potentially incorrect behavior. In the memory category, we have three classes. The first is addressing, and our focus is on pointer creation and pointer modification. And our concerns are that we're going to have out-of-bounds access or are going to be pointing to the wrong object. The management class is focused on allocation, resizing, and deallocation of memory. The concerns here are that we'll end up with memory exhaustion or insufficiently sized allocations. Finally, we've got memory use, and here we're thinking about initialization and access, the read and write of the memory. Our concerns are that we'll have uninitialized memory or memory corruption. Our final category is data. It has four classes. We have the declaration class, where our focus is the definition of data. Here we're concerned that we have incorrect object definitions. We have name resolution, and its focus is type object binding. The concern here is that we'll end up with the wrong binding. This can occur with the casting of objects with inheritance. Next is type computation, focused on type-based calculations, where we're dealing with things like array handling and offsets. Our concern here is that we'll end up with incorrect results from that. And finally, we have type conversion, where our focus is, as the name says, on type conversion, and we can have either data errors or type errors. Now, one may look at these various classes and ask, what about undefined behavior and other things that can go wrong? From the standpoint of cybersecurity, we're not concerned with things which aren't directly cybersecurity relevant. These are things which we don't have direct controls for. There are plenty of switches and issues which have to do with code soundness, and that's fine, but that's not cybersecurity relevant. It's important as a cybersecurity SME not to overreach into other people's backyards. There's a tendency to do this because you think, well, I'm here, I can look at this, I can make this happen. The fact of the matter is that there's plenty of work for cybersecurity to do without taking on the work of other groups. Here we see our option sheet extended with the bug classes for each of the various options. As a reminder, the bug class is not there merely for a documentation purpose. When we categorize which bucket each option goes into, and when we select the options to use, we'll have more information to base those decisions on. The next column in the sheet is that of the category into which the option will fall. We're not going to touch on this here because that's the subject of the next activity. This brings us to the final column, and that is notes. We use this column to provide reference or background material specific to the option. For instance, if we look at GCC05, the shift overflow, in addition to the description saying that it's relevant because we care about the data overflows, and the bug class being memory use, we can indicate that its focus is CWE 190, integer overflows, or wraparound. Additionally, the option may be supported by multiple things. If we look at GCC06, which is zero length bounds, which is memory addressing, we have both CWE 125, out of bounds read, and CWE 7087, out of bounds write. Hopefully you'll appreciate that although perhaps time consuming depending on the tool, that option identification is a straightforward activity. From the standpoint of being able to justify why particular options are being used, this is a good exercise to go through. Now let's do a quick recap of the steps that we used. We're going to start by identifying the cybersecurity options. We'll then provide the reason the option is relevant from a cybersecurity perspective. We then assign a bug class to each option. And finally, we'll include any supporting references. The materials that were used to cover this example are in the location shown here. It's important to note that the workbook includes all the sheets covered in this training. For additional information and to get a more in-depth set of references, the Secure Settings Identify Options Procedure tertiary document is available in the AVCDL GitHub repository. All AVCDL materials, both in source and distribution forms, are available on our GitHub site as shown here. Because of the size of the repository, it's recommended that you either clone the repository or download a zip archive of it if you're not familiar with using Git. Instructions for downloading a zip archive are linked to on the repository's front page. Videos covering various aspects of the AVCDL are available on our YouTube channel as shown here. It's important to note that all AVCDL materials except for the introductory blog posts are intended for product cybersecurity engineering practitioners. With this training complete, if you've completed the other trainings covering the secure settings process activities, you can proceed to the other training at this level, Secure Design Review. Additionally, if you've completed threat prioritization, you can also proceed to attack surface analysis, threat modeling, penetration testing, and vulnerability identification. Additionally, you can proceed to either code reuse or secure coding. Here are the references to the source material used in the creation of this presentation. They'll also be included in the video description. Additionally, this presentation source material will be provided on the AVCDL Git repository.